We ordinarily don't think of dilute solutions as being particularly different from, say, the pure solvent because it just involves a little bit of the solute particles mixed in with that solvent. However, there are some special properties that we observe for these kinds of solutions, and I want to talk about one of those in this video, the colligative properties. Now, let me first start off by saying that colligative properties are ones that depend only on the amount of the solute and not on its identity. So by amount, I mean like number of particles and things like that. So it basically doesn't matter what you mix in with the solvent. These solute particles, whatever they may be, will change the properties of the solvent in some ways that we can actually observe. Now, some of these colligative properties include things like the freezing point depression or the boiling point elevation. There are some others as well, but I want to focus on those in this particular video because they involve phase changes that we know something about and we know how to treat. So when we think about, for example, the freezing point of a solution, all right, what happens at that freezing point? And what could possibly change about that freezing point when we have a solute present? Well, part of what we're interested in doing here is relating how the solute will affect, for example, the temperature at which the freezing point would occur. And that, of course, is related to a phase equilibrium between a solid and a liquid. A phase equilibrium which we know is defined by an equality of the chemical potential. So we know at the freezing point, for example, that the chemical potential of the solid that's produced is going to be equal at that point to the solution. All right, this is something that we have in phase equilibrium. But we also know that the chemical potential of the solution can be written as the chemical potential of its pure substance plus RT times the log of its activity. Now, in this case, I want to make a special note of what this quantity is, the chemical potential of the pure substance. That's really the chemical potential of the pure liquid. So in effect, what we're doing is we are relating the chemical potential of the solid and the liquid here to one another. And the activity is the only thing that contains something that is relevant to the solute. So it is the action that the activity will take in this balance between the two chemical potentials that will alter its temperature. So one way we can get a handle on this is let's separate and isolate the activity on one side. So in other words, the log of the activity is going to be the chemical potential of the solid minus the chemical potential of the liquid. Now I'm just changing this for chemical potential of the liquid in this case. All right, divided by RT. All right, so we have now a way that we can begin to relate this chemical activity, which tells us something about the solution, with the conditions that are relevant to a phase equilibrium for freezing. Now, what we're interested in is the effects of temperature. So one way we might get a handle on that is by differentiating this equation with respect to temperature. But I want to make a special note here, and that is if I differentiate with respect to temperature of a quantity that looks like mu over temperature, well, the mu, in effect, is just the molar free energy, molar Gibbs energy. So that's essentially the same as taking this derivative. But we already know what this result is from the Gibbs-Helmholtz equation. We found that a couple of modules ago and found that, in fact, that when we take this derivative is equal to the molar enthalpy divided by the temperature squared with a minus sign in front. So this result from the Gibbs-Helmholtz equation is something that we can use to get a handle on the temperature dependence of the activity in this case. So now if I take the derivative of the activity, so d log of activity with respect to temperature, and we'll do all of this at constant pressure, it's going to be equal to 1 over r. Okay, that's a piece that I did not include in this differential here. And then when I plug in this chemical potential over temperature here for the solid and the liquid, as I've done here, I'm going to get from the Gibbs-Helmholtz equation that this is just equal to the negative of the molar entropy molar enthalpy, sorry, of the solvent, of the solid. Okay, and that's going to be divided by the temperature squared. So all I've done is translate the Gibbs-Helmholtz equation in when I take the derivative of this expression with respect to temperature. Okay, minus or plus the molar enthalpy of the liquid for the solvent over temperature squared. So I'll get an expression that looks like this. All right, now let's rearrange this just a little bit to write it something like this: minus 1 over RT squared times the, actually let me keep the plus out here and make this the enthalpy of the liquid minus the enthalpy of the solid. And I'll note that this thing that we have here is just the enthalpy change for the fusion of that substance. So in other words, I can write this as 1 over RT squared delta fusion of the molar enthalpy for substance 1, which is our solvent. All right, so this is a very nice relationship between the temperature derivative of the log of the activity and the fusion enthalpy, the change in fusion enthalpy for our solvent. All right, now how can we utilize this a little bit further? Well, a couple of things that I want to do. One, I'm going to move the dt here over to the other side, because what I ultimately want to do is to integrate my equation, my d log a1. I want to integrate this from the perfect, or I should say the pure substance. So the activity for that has a value of 1 to its value when we have a solution. Okay, so that's what the temperatures of which I'm going to be integrating over here. So I'm going to have an integral now from the fusion temperature of the pure substance to the fusion temperature now of the solution. Okay, so be clear about those integration limits. And then the thing that I'm integrating is this function dt. So I'll have 1 over RT squared delta fusion of the molar enthalpy dt. Now we'll make the assumption that this temperature change is not, this temperature difference, this integration range is not going to be very large. And that's generally true for dilute solutions. They're not going to change the fusion temperature very much when they act. So that means that this enthalpy change is not really going to change very much at all either. And obviously the gas constant won't either. So we can bring these things outside the integral sign. So I'll make this delta H a fusion over R, and the integral will simply be from T fusion of the pure substance to T fusion of the solution of dt, and I'll make that dt prime over T prime. All right, and I already know how to do that. It's just going to be 1 over T prime, 1 over T squared. So I'll end up with a result that looks like this: delta H fusion over R, and there will be a minus sign now because I've got 1 over T, so it'll be minus 1 over T squared. And now I'll have 1 over T of fusion of the solution minus 1 over T fusion of the pure solvent. Okay, so that's going to be what I get when I integrate this over temperature. What about this other side when I integrate it? Well, I'll end up with log of A1 evaluated from 1 to A, okay, but log of 1 is just 0, so that's really just going to give me log of A. And I'm going to continue to label it as log of A1 because I want to keep referencing the solvent. Now we also know in the pure limit that this goes as log of x1. But we've shown before that we can when we write this in terms of the mole fraction of component 2, that is of the solute, that this actually can be written as minus x2 because it's very small. So in effect, what I have now is a result that says that x2, because I've got a minus sign there and a minus sign here, x2 is equal to delta fusion of the molar enthalpy over R times 1 over T fusion of the solution minus T fusion of the pure solvent. Okay, and this is, I think, worthy of boxing, as it is a good result. Okay, what does this tell us, though, about the relative temperature of fusion for the solution versus the temperature of fusion for the pure substance? Well, this is a positive quantity, the mole fraction of X2, and this is a positive quantity, the delta H over R. So both of these are positive, so that means this must be positive also. So I must have that 1 over T fusion solution is minus 1 over T fusion of the pure substance is greater than 0. But this means that 1 over T fusion of the pure solvent is less than 1 over T fusion of the solution. Now, if you think about this, what that means is that this number has to be larger than that number. All right, or if I move these up to opposite sides, essentially what I would have is that T fusion for the pure substance is going to be greater than T fusion for the solution. In other words, the freezing point decreases. Okay, well, this is actually in accord with what we know about solutions. We call it freezing point depression is a colligative property. And so in this case, the freezing point decreases as a result of adding a small amount of solute to this. Now, we can actually develop this a little bit further. For example, if I take this quantity here and rewrite it a little bit, I could rewrite this as T fusion of the pure solvent minus T fusion of the solution over the product of the two. But if this is just a small change, I can approximate that as being just the T fusion of the pure solvent squared. Okay, so I've already indicated that this is going to be greater than this, so this is a positive quantity. I'm going to rewrite the numerator as delta T fusion, and this is going to be over T fusion of the pure solvent squared. All right, so if I have that as over here on the right-hand side of my equation, now what I need to do is think about how I can cast this mole fraction of X2 in terms of the concentration. Well, we already know how to do that also. And I'll just remind you that the mole fraction of X2 in terms of the concentration is going to be the molality divided by essentially 1,000 over the molecular weight of the solvent plus the molality. If we're in water, this will in effect be equal to the molality over 55.508. All right, so we have a direct way of getting that. I think another way we could write this, if we don't want to necessarily limit ourselves to water, is it would be the molality times the molecular weight of whatever solvent we happen to have divided by 1,000. So now we can substitute this in for our X2 over here and solve for the actual change in the temperature of fusion. All right, I'm going to have to do that on the next page, so I hope you'll allow me to skip over there and finish out this line of thought. So when I write out the change in the temperature of fusion, now in terms of all those other quantities I have, and solve for it on one side of the equation, what I'm going to get is an equation that looks like this. The molecular weight of the solvent divided by 1,000. So in other words, we're expressing the solvent in units of kilograms, times R times the temperature of fusion of the pure solvent squared divided by the fusion change in enthalpy for a molar amount. And this will all be times the molality of the solvent, molality of the solution. Well, I hope this looks familiar because what we've written here is essentially, if all of this is captured together as one constant, what we've written here is an equation that you may have seen in general chemistry, that basically the change in the fusion temperature is equal to a constant times the molality. the constant in this case now has been specified in terms of these other quantities, so you can see where it comes from and also what sort of factors it might influence its relative magnitude. For example, heavier solvents should increase the magnitude of this freezing point depression. If we have a higher fusion temperature, that also should show a larger freezing point depression upon this. For delta H of fusion, if we have a smaller enthalpy of fusion, we'll see a larger effect. So smaller delta H fusion leads to a larger delta T, larger T fusion, and larger molecular weight lead to it. So it gives us an idea of how to interpret this and actually relate it to different qualities that we might have for our solvent. I want to parenthetically note that a related phenomenon, related colligative property, is boiling point elevation. And we could use exactly this same development to derive a very similar formula for that. In this case, though, however, because liquid liquid is the initial state and vapor is the final state, it's going to reverse the sign of the delta T. So in this case, we find that delta T for vaporization is not negative, it's actually positive. That is to say, the T vapor for the solution will be greater than T vapor for the pure substance. Okay, and an expression for that can be written as follows, very similar to this above expression. It's going to be the molecular weight of the solvent times R times the vaporization temperature of the pure solvent squared over the vaporization enthalpy. Okay, and again, up here, this change is smaller than zero. This change will be greater than zero, and I forgot to add the enthalpy. The molality. And sometimes this is also written this way in general chemistry books. All right, so this here is what defines the boiling point elevation constant for a given substance. Okay, it is a quality of the solvent and independent of the identity of the solute.